17, number 4. Oh, so they refer back to exercise 1. Blah, 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 blah. So suppose the poll results were obtained by mailing 100,000 questionnaires and receiving 21,944 responses. Is the result a good estimate?
No.
Why not?
Voluntary sample response.
Exactly. I don't care how large your sample is. If it's selected poorly, and in this case it's a voluntary response sample, so I can't trust it. I don't care how large it is. It's just a lot of angry people maybe. And there are a lot of angry people. So you can have a very large group, but they're going to be biased. Maybe not, but I have to assume it is, because of the way it was selected.
Could you do 7.3, number 2 and 7? They should be pretty quick.
Okay. So on page 339, number 2. Oh, okay. I love this. A design engineer for Ford Motor Company must estimate the mean leg length of all adults. Now, why would somebody working at Ford Motor Company be interested in that?
So you reach the pedals?
Yeah, exactly. Want to design a car where most people can comfortably fit in the front seat and still reach the pedals, right? They're not going to catch everybody. There are people at the extremes, right? Little grandmas looking to the top. I can't. Can you put a block in there? But obviously they want to try to get it set up so that the majority of people can fit comfortably. She obtains a list of the 1,275 employees at her facility, then obtains a random sample of 50 employees. If she uses a sample to construct a 95% confidence interval, blah, 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 will her estimate be good? I mean, it sounds like she did a great job. She obtained a list of all the people. She randomly selected 50 people. 50 is bigger than 30. Everything sounds fantastic, except what I just said. Would that 80-year-old grandma be working there? Would she be represented? No. In fact, so anytime you're trying to say something about who's the audience she's talking about, who's the population that's going to benefit from their product? Everywhere they sell a Ford. Everyone who has a possible access to buying a Ford product, right? Ford vehicle. So if she only samples the people at her facility, the results are going to speak only to the people that works at the facility. And they obviously are there for a common purpose. They work for Ford at that place. So will her estimates be good for her intentions, which is to try to get most people to feel good in that car? No. She's not sampling the whole population, is she? She's only sampling a subgroup of the population. That's not good. So it's just like if I wanted to say something about how the U.S. feels about Mitt Romney, and I go talk to people, 8,000 people I talked to from Los Angeles, just to pick somewhere. Obviously, I can't say a damn thing about the United States. I can say it looks like people in Los Angeles feel this way, but I can't say it looks like people in the U.S. feel this way. That would be insane, right? So here she needs to sample from the true population, which is everybody that could buy a Ford. Okay. Harder work, but it would make the results actually something you could use. Does that make sense? So it felt a lot like the last one. It was the poor choice of sampling. The last one was voluntary response. This one just sucked because they did basically a convenient sample. It was really convenient. They were all there. Number 7.
Yeah.
Oh, I'm glad this came up. I really... here's what the book shows you as being the formula for this. So let me focus on this. And how do we find this easier? If I wanted to get like let's do a little review. So everybody's like, what the... Yeah. So how do I find, if I want to get like an 87% confidence interval? Here's a good little review. If I want an 87% confidence interval, can you guys take a minute and not say anything and figure out what the z-score is? Probably want to do some of this and some of this in the book. what would that 87%, what would the z-score be for that? All right, so who thinks they have it?
1.51?
0.51?
1.51.
1.51?
Yeah.
All right, so how did you guys get that?
Divided by 2.
Yeah, if there's 87% in there, then how much is out here?
6.5% each.
13%. And that 13%, and this is kind of nice that this is coming up now, because in chapter 8, this is going to rule our lives. This little symbol. The amount of area that's in the tail or tails, and these always have 2 tails, you see that? That's given the symbol alpha. So in this case, alpha is 13%. So that's the little symbol alpha just means the area that's in the tails. That's the first thing we do to the 13% to try to find this number. You guys already said it. What do you do to the 13%?
Divide by 2.
Cut in half. So you do alpha, cut in half. 6.5% or 0.065. So do you see this symbol? I hate that they use this symbol because a lot of students, they think that this means I got to plug stuff in here. No, it means the z-score that goes with alpha over 2, that goes with this percentage. So it speaks more to the process that we go through. So it's a subscript because it's not just any z-score, it's a specific z-score. It relates to how confident you want to be. That's why it's got a little subscript on it. But there's really no need for that. I already know it's going to be the z-score I want. Right? That's why I write the formula just like that. This little thing does not mean plug anything in there. It just means find the z-score by doing this. Cutting that area in half and then looking it up. Is that cool?
So alpha is the tail.
Alpha is the amount that's in the tail or tails. In this case, there are 2 tails. So alpha is the total amount out there. I like it. So to come back a step, they say find.
Yeah, that's 7.397.
Can you draw the picture that relate to the alpha equal to 0.20? What does that mean? What does alpha equal to 0.20 mean?
20% is not included.
20% is outside. So what confidence interval would this be? 80%. If there's 20% outside, that's what alpha means. The amount outside in the tails, there must be 80% in the middle. So this would relate to an 80% confidence interval. Cool. So now just find it. Now the first step, of course, and again, the little symbol here tells you what to do, but I'd rather us just know the process and have a z-score sitting in that formula so don't freak out when we see this. Oh shit, I got to put stuff in there. No. What's the very first thing you do if this is an 80%? 20% out there, so of course 10% down there. And then you can look that bad boy up. How are we doing? 20 out there, 10 on that side. Look it up. Cool. So do not make too much out of that z-score with a little alpha over 2. A lot of people are like, what's that little fish symbol? What the hell? Yeah.
So we can actually set up a table for z alpha over 2.
Sure.
I see like people come.
Well, there's a lot of different ways people have decided to represent the z-chart. And
I think that's kind of like cheating. I think that's kind of like cheating that they have that chart.
Kidding?
Cheating.
Oh, cheating. Yes. In a way. But anyway.
And then you have to use it.
What do you guys get when you look that up? 0.10. Sorry.
I think negative 1.228.
So 1.28. Should be plus or minus 1.28. Cool. Yeah.
I had a question on the sheet that we did yesterday.
Yeah.
On 1B, you put 100 min, but
Oh, what the
I
hell?
just rounded up.
It should be 97, yeah.
Okay.
I don't know why I put 100.
I was wondering.
Should be 97.
Okay.
I just really rounded the hell out of it.
I was like,
It should be, yeah. So on that sheet, it should say up to 97. Thank you. So it's always rounding up. Cool, I like it, but not that much. Yeah. All right, so any other questions from homework? Okay. It's encouraging to me that there were some questions, so people are getting into this. So don't forget that we haven't really fully gotten all the way through 7.2 yet. So if you're trying 7.2 homework out, there might be a few that you don't know how to do yet. Yeah?
Can you go over 7 to number 6?
So let me see if I'm looking at the right. Yep. That one's the same idea. How do you get a 99.5% confidence level, right? So how would you find the z-score for that? How much must be out here?
0.
Yeah, it would be out here. Total alpha would be what in this case? Alpha. Total alpha would be 0.005. So alpha over 2 would be 0.025 in this one tail. So now you got to get the closest you can to 0.025. So I want you to realize something. As we do more and more of this, you guys are going to start to remember some of these things. This is 1645. This is 1956. This is 2575. So what do you know for sure, without doing any work, what do you know about the z-score for 99.5% confidence? It should be how related to this, for example?
Higher.
It should be bigger, right? If I want to be a little more confident, I got to go a little further out. Therefore, it should be maybe 2.6, 2.7, I don't know, right? Do you guys see? Where should 92% confidence level, what's z-score should that be? Between, yeah, 92% should be between 1.645 and 1.96. So there's a way you can at least tell if what you found makes sense. So we did 80% over there. 80% we got was 1.28. That at least makes sense that it's well below that. I don't have to go anywhere near as far out just to catch 80% compared to 90%. Maybe. So the idea here is pretty simple. We know that most of the data values should be close to the mean in a normal distribution, right? Most of them should be close to the mean, and as you go out further, there's less and less and less. So of course, if I want to catch more and more and more, I've got to go a little further away from the mean. So my z-score is going to go a little bigger, a little further away to catch a little bit more, catch a little bit more. Okay, good. So if I ask you to find a 97%, you know the z-score is going to come in between those to make sure that it makes sense. Did we actually look that up? What do you get for that one? 0.0025? 2.81?
Yeah.
Okay. So that makes sense. Cool. I like that you're repeating with something else. All right. So any other questions before we, yeah?
11. 7.2.
Oh, this is a question I could ask you in like a algebra class, actually. I have to explain a little bit, but still. So why are there two sides to this thing? Why does every confidence interval going to have two sides?
Z-score?
There's two z-scores, and in fact, from the formula, you can see there's a plus or minus. There's a lower edge and an upper edge. Sort of like we've known that for a long time, ever since we first talked about unusual values. Go up and down 2, and anything outside of there is unusual. Confidence level is just kind of is more specific. It doesn't say it's always 2. Sometimes it's 1.96. Sometimes it's 2.575. We kind of redefine it as we need. That's why there's two sides. So this is up from the middle and this is down from the middle. The same amount, of course, right? The error is the same, up and down. So how do you find that middle? Yeah, how do you find the middle of any two numbers? Add them, divide by 2. Find the average. So what must p hat be right in the middle? What's p hat?
0.483.
483? Yep. And then how do you find the error?
Subtract the lower from that.
Yeah, there's two different ways. You could actually do the subtraction here and cut it in half. Is that cool? If I normally go p hat plus e up and minus e down, if I do this distance, can I just cut in half to get the error? Or now that I have this dude, I can just see how far away is he from that.
0.046.
So the error would have to be 0.483 minus 0.437, 0.046. Cool. Do you guys see that question? I could actually kind of, if I set it up correctly, I could ask that question in Math 103 or whatever. It's just playing with the numbers. Can you find the middle of these, and can you see how far each one is away from the middle? Cool. Yeah.
Center radius.
Where does x bar and p hat, if I give you a confidence interval, where must it sit in the confidence interval? It has to be right in the middle. Because what do I do to it to get the confidence interval, the numbers? I add and subtract the same thing. So I just average the two. It's got to be the number right in the middle. Cool.
So if you draw the little graph and you put the two z-scores, it would have to fall. It's kind of like the mean has to fall in the middle.
Exactly. I like it. Is that all right? No?
I'm just curious because I didn't get like you add the 2 and divide by 2.
Yeah, so you do this in the calculator. So be really careful. You didn't get 0.6 something, did you? Okay. It's those parentheses. Otherwise, the calculator does this. Cool. Okay. So be really careful. That really sucks. Trust me. When you do the whole problem right, you just left your parentheses off. And of course, that's outside the interval itself. That couldn't possibly be. Yeah. All right. Any other questions before we? Someday somebody's just going to say, just ask him everything.
Yes.
No.
Your homework done.
All right. So the only last thing, let me do a little review. So far we've talked about this here and this here. And these are both obviously confidence interval problems because they have plus or minuses in them. They're going to go up and down. They're going to capture something. This one you use when I ask you to find a confidence interval for a mean, and this one I use when I ask you for a percentage. Right. So when you're doing when you're doing a test or something, you say which one do I use? Well, did I ask you for means or did I ask you for percentages? That tells you which one to use.
Can you give us example questions for both of them?
Right now. Yes, I could.
Just questions. Doesn't really have to answer.
The great thing about the questions is I can't help but be completely obvious. I'm going to say find a 99% confidence interval for the true mean. Oh, that one. Right?
And then the other one.
Find the 99% confidence interval for the true proportion or percentage. Oh, that one. So you can't make that any better as to how to tell which one of those to use.
Guess I'm having trouble understanding what exactly
Okay. Or just ask me. Yeah. What I want to focus on today is there's one last thing to do in 7.2, and then we're going to add a third option here. Because to be completely honest, this one is if I want to do the mean, but sigma is known. And I want you to realize in general, do we know the population standard deviation somehow magically? I mean, this is if I know the sample mean, but I want to kind of estimate what the real population mean is. Why the hell would I somehow know what the standard deviation is? for the population. You with me? Now there are certain situations where it makes total sense. If I want to find the 98% confidence interval for the true height of all men who attend Grossmont, I know the standard deviation of all men's heights for all of the U.S., right? So that's one situation where it makes sense. But normally I'm looking at a population that I don't know shit about. I'm just taking a sample and I'm trying to say what's going on. I normally don't know this. So there's a little tiny change if I only know S, the sample standard deviation, which is more honest. That's normally what we know. We don't normally know the standard deviation of the population. So that's part of what we're going to talk about today, and that's section 7.4. But the first thing I want to do is finish out 7.2. And this should hopefully be relatively quick. If I want to do the similar thing that we did last time with this formula we got last time, when do I use that formula?
You don't know the sample size?
Yeah, I mean the formula tells you what variable is it solved for. N. Okay, so that must be used when they're asking me how large of a sample must you take to blah blah blah. Right? And the magic word there is within. If I want to be within 2 inches of the real height of men, E would be 2. On the handout, E was 0.5. I want to be within half an inch. So I want to do a similar thing over there. What if I want to be within 2% of the true percentage of Grossmont students who smoke or who whatever? I want to do the same kind of thing. I want to know how large of a sample. To be within something percent. So we do just like we did before. We do a little bit of algebra. This one seems like it might be harder, but not really. What part of that equation is the error? Well, it's probably the part that I already told you is the error. So if I say the error is this, I'm trying to solve for n. Looks kind of disgusting.
Didn't you already give us this?
No, I gave you this. We haven't talked about that one yet. For this. This is finding n when I'm talking about sample means. I need a similar formula for when I'm talking about percentages. You with me? When I'm talking about NPQ problems, are they going to give me this? For an NPQ problem, I can find my own standard deviation, can't I? What would that be? NPQ. And now when I'm talking about confidence intervals, now we can kind of see how it changes a little bit. And this is kind of cool. How does that standard deviation change a little bit? I divided by root n, right? How does this change a little bit in this formula? It's sort of the same idea. I kind of divide by root n. It's kind of nifty. There's this nice symmetry there. So now this is my standard deviation. Oh, sorry. This piece is my standard deviation. So when I'm talking about how large of a sample do you have to be within 3 inches of the real average height, you'd use this one because you would have a standard deviation. If I'm talking about I want to be within 3% of the true percentage, you obviously want to use the one that's got percentages in it, which is what this is going to be. So a possible good first step here is to square everything. Is that cool? Just to get that square root the hell out of the way first. So on this side I get this here. Is that cool? Because the square root and the square cancel. Now how do I solve for n? What's kind of the shortcut there? How do I solve for n?
Multiply place side.
Yeah, I multiply the n up and I divide the e squared down, so I end up with this. And again, that's a formula that you could put on your formula sheet. So let me show you what we would do in the real world with this kind of thing. And I want to see what you guys think about this. How large of a sample? To be within 7% of true percentage who have started Chapter 7 homework. Let's say this is at 95% confidence. Why do I have to tell you that last bit? What is that going to help me fill in the formula? The z-score. I always got to give you the confidence level I want to be at. That's what tells us what the z-score is. So notice, if I want to be more confident, what happens to my z-score? If I want to be more and more and more confident, my z-score has to keep getting bigger and bigger and bigger. Now watch, if I put bigger and bigger numbers here, what happens to my n? It gets bigger. Now doesn't that make sense? To be more confident about what you're looking at, wouldn't you have to get more in your sample? Okay. So what do we know from this? What's z going to be for my 95% confidence? 1.96. I kind of gave you a little cheat sheet earlier, if you noticed. Of z-scores. No, definitely not. But there's a lot of them on your z-score chart, which you're going to get anyway. So hey. What else do I know for sure? It's kind of funny because I don't know much.
7% for error.
Good. Error is 0.07. Is that cool? I want to be within 7%. So I want to be 7% off at most. Now, here's the part that I want to explain from the book, because I don't think they really explained this very well. If you don't know the percentage of anything, what's your best guess? 50-50. Right? What percentage? I got to have some kind of p-hat. I got to have something to plug in there. And if I don't have a clue what it is, I use 50%. Now here's the cool thing. What I'm going to do is I'm going to fill in an actual value. For those of you that are at all interested, 50% for P and Q makes N the biggest it has to be. And I want to make this point. If there's ever something you don't know about a problem, you have to be conservative on everything else. So if you don't have a freaking clue what p-hat might be, shouldn't you be forced to take the biggest sample you might have to take? So putting 0.5 and 0.5 here makes N the biggest it could possibly be. If I somehow knew it was 20% and 80%, that would make this a little bit smaller. Okay, so there's a part in the book where they have this formula here. Can anybody tell me where that might have come from, based on what I just said?
The fact that 0.5 times 0.5 is
Yeah, if you don't know, so that this is written, if you don't know what p-hat and q-hat are, you use this formula. Where the hell did 0.25 come from? Well, what's 0.5 times 0.5? What's a half times a half? A quarter. So if you just put a half in for p and q, that'll end up at a quarter at the end. So if they don't give you any idea what p-hat and q-hat are, and they're asking you this kind of question, you have to guess that it's 50%. And some of you might, if I was you, I'd say, why the hell are you allowed to do that, Jeff? That should be allowed. You don't know. Why should you? Because mathematically, it forces me to take the biggest possible sample. So I am still being as conservative as possible. So let's try this out now. Let's see what we get. Z squared, so my Z was 1.96. 50 times 50 is 0.25. My error was 7%. So somebody help me out there. How large of a sample?
196. Really?
Yeah, that would be, let's see, 1 divided by
Yeah, 196.
yeah, almost 200, yeah. 196? So does it come out to be what exactly?
Just 196.
Exactly 196. Cool. All right. I like it. Yeah.
Sorry, where's the 0.25 coming from?
So just to make it back up a second, we don't know what P hat and Q hat are, so we do have to say that they're each 0.5. And that was just me skipping a step like the book does. Half times a half is a quarter. So that would be 0.25 there, not a big deal. Yeah, so if you'd rather just put that in there all the time, you're fine. And to tell you honestly, I really don't like that formula. It makes it look like it's totally different for some reason. And it isn't. It's still P and Q, just saying that they're both 50-50 because you don't have a clue. All right, now, what if we knew, like I take a survey. Let's say I survey 10 people. And 7 of them have started. Chapter 7 homework. What's P hat? Yeah, 7 out of 10, 70%. So what's Q hat? 0.3. So in the real world, this is kind of neat. You can take a small sample to get an estimate for P hat and Q hat. So then you use those estimates in your formula to see how large of a sample you really should take in the end. You kind of with me? No. We all love this stuff so much. I hope that kind of makes sense, that if you don't know something, you're going to have to guess 50-50. That's the best you can do. Over there, I'm actually taking a little sample just to get a feel for what P hat and Q hat might be. And then I can plug those in here to get a better estimate for my N. So what would N be now? Z is still 1.96. What's P hat and Q hat now? 0.7. 0.7 and 0.3. And my error, I still want to be within 7%. So let's see if I was right. We should get a smaller number than 196. That was my conservative estimate, not knowing a damn thing. Now I go in knowing a little something. I talked to 10 people. I have some idea. So about 165?
Yeah.
So it's a little arrow. 165. So a little bit less, right? Cool. So that's the difference between those two formulas. There aren't really two formulas. There's one formula where if you don't know P and Q, you got to assume 50-50. If you do, you plug those in into that one single formula. Cool. Okay.
We get a bonus question on the test that asks to show that 50-50 maximizes error.
I'll think about it.
Make it easy. All this bonus question are sentences. They're not math.
You're starting to notice something, yes. Now, if I said that the only difference that I want to make is right here. If I told you, I'm telling you straight ahead of time because I want to make sure that you understand before I get into the discussion of why this is the way it is. If I told you right now, the only difference in 7.4 is we're not going to look at the z-score chart to get the number that goes there. We're going to look at another chart. And actually that chart is easier to read. Would that really trip anybody out? I mean, I think we're all able to find the z-scores. This is what I'm going to assume. If you're not, you desperately need to come see me. So if I told you 88% confidence, you could find the z-score that goes here, right? So if I told you I'm not going to change anything else in the whole problem except you're going to look at a different chart to get the number here, that should not be like majorly bad news, I'm hoping. So why in the world would this change in this case? If I don't know sigma, and I only know S, and again, what's the difference between those two? Population is that one, this is the sample standard deviation. So if I only know the sample standard deviation, how should my confidence interval compare? So if I made a confidence interval thinking that it was this, and I went from like 2 to 7, thinking that I had the population standard deviation, and then I go, oh crap, I don't know the standard deviation of the population. I only have this, which is only an estimate. What should happen to my confidence interval to reflect that thing that I don't know for sure?
Less confident.
Now, I can't change my confidence level. I still want to say I'm 95% confident or 98% confident. But if there's a piece of this that I'm not sure about,
Error.
what should happen to my confidence interval to cover me for that?
Error.
What about my error?
Your error should get bigger.
Bigger. So the confidence interval should get bigger. How are we doing just on that piece right there? So if there's anything about my problem that I am not as sure about, I have to be more conservative in my work. So I would have to say, oh crap, it's not that. Maybe it's going to have to be 1 to 8 or something, depending on the work. I don't know. So for for example, for 95% confidence, the z-score is 1.96. The score I'm going to use here should be bigger than that. And that is to help cover my ass for the fact that there's more stuff I don't know for sure. How does that by itself sit with you guys? Is that all right? Does it kind of make sense? I know it's difficult. This class is one of the few math courses you hit where I can't just talk about work, work, work. I have to step back and talk about what the hell does it mean, what the hell does it mean, what the hell does it mean. And it's hard to kind of get those two things together in your mind when you're learning it. But the idea that this has to go a little bit more out to cover for the fact that I'm not sure about something I'm using, that by itself should make sense. Now, what does that mean mathematically? The number I use here should not be this. It should be a little higher. And what we call that now is a t-score. T-scores will always be a little bigger, or maybe a lot bigger, than what the z-score would have been. When do you think I need a really big-ass t-score? When I have a really what size sample? Small sample. So it seems like the t-score should itself get smaller as my sample gets bigger. So let me show you this chart to show you everything we just talked about and how it shows up on the chart.
Is there a formula for t-score?
Yes, but we're not going to even look at that one.
Alright, so it's like the formula for z-score.
That's worse, but yeah. Worse in the sense that it's got more involved. So for those of you who have your book, this is just, if you go to the z-score chart in the back, flip one page in. That's the chart we're going to use here. And I want you to realize something. On your formula sheet, you're going to have this. And you're going to have this. You see how the formula tells you when to use t-scores. When to use t-scores. When you only have S, not sigma. Bam! I mean, I keep trying to point this out, and I noticed on YouTube, somebody put a comment, here's Jeff showing people how to cheat. But it's not how to cheat, it's how to be smart about what I allow you to use. The formulas tell you what to do when. And that's the worst part about math, is what the hell do I do when? So when I know the population standard deviation, z-scores. When I don't know the population standard deviation, t-scores. Well, what's got to be true no matter which one you want to use? What's got to be true? What's the big important thing that has to be true for me to do any of this stuff? What's got to be true about my distribution? Has to be normal. What the hell is that? Fire. All right. So, the really cool backstory to the T-score, by the way, and believe it or not, there is a cool backstory to this thing. It was made by a person working at the Guinness Brewery. Anybody enjoy Guinness? Okay. And he actually was doing a study that Guinness didn't really want him to publish, but he wanted to do this thing, so he actually called himself student. He gave himself what do you call it?
A pen name.
Pen name, I like it, whatever. Just to cover himself so they wouldn't know it was him. So this is very often referred to as the student's T distribution. And it's because it was his, why is that word going? Alias, there it is. I keep thinking anonymous, that's not what that's his alias that he used, the student T distribution. So this was created by a dude working at Guinness Brewery, these T-scores.
How long ago was this? Wasn't that long ago.
I think it's the late 1800s, early 1900s, somewhere around there. But don't hold me to that.
I guess it's safe to say that beer induces creativity.
I don't know if it's safe to say that, but
Yeah,
that is something you can say.
Yesterday.
Okay, so can you guys see that okay? Might be a little blurry. No, is that bad?
The light maybe?
You need the lights off?
The gammas.
Thanks, man. All right. So here's what I want you to realize. If I wanted to make, and this chart is a lot more detailed than we need it to be right now, but once we get into chapter 8, we're going to use everything on this bad boy, right? Well, the first thing I want to point out is, let me do this first. If I wanted to be 95% confident about something, which column do you think I would use? If I want to be 95% confident about something, which column goes with that?
0.05, 2 tail.
Yeah, the middle one, right? This guy. If I want to be 95% confident, how much is outside in 2 tails? 5%. 5% in 2 tails. How much is in 1 tail? 2.5%. Same damn column, right? Can't go wrong whichever way you look at it. How we doing so far? So they don't have confidence interval numbers up there. It's too bad. If I want to be 80% confident, I would use which column?
Last one.
The last column, because that would have 20% outside. Okay. Let's see, I got to unfreeze it for a second. I want you to notice one thing about, let's look at this right now. For like a 95% confidence, if I have a sample size, a really small sample size, what's my T-score going to be? Like 12. That's crazy huge. But what happens as my sample gets bigger and bigger and bigger? It keeps getting smaller and smaller and smaller. Look all the way at the bottom. One thing I love about this chart is way at the bottom it says large sample. But look for 95%. What does that look like? Well, actually not much at the moment. There it is. 1.96. Isn't that the Z-score?
Yeah.
So when I have very small samples, the score that I use in the formula has to be bigger than it normally would be. The bigger my sample gets, the closer that gets to this. Because the more I should be allowed to use the Z-score. Because the bigger the sample gets, the more certain I am about that standard deviation that I have. So when your sample gets large, and they purposely don't define it, when your sample gets large, I can actually just go ahead and use the Z-score.
So we do have the option to use it.
Obviously, one part of it is above 2,000. Yeah.
So we do have the option to use these scores.
If the sample is above 2,000 or close enough for whatever you're doing, right? Some teachers say you start, holy crap. Some teachers say you start using Z-scores when you hit 30. Why do I disagree with that? Z-score for this would be 1.96. The T-score at 30 would be 2.042. That's pretty damn far apart, actually. So that's why I use the whole damn thing. There's one other thing I need to talk about before we really get into this chart. Degrees of freedom. And I think I talked about this before. I can't remember if I used that same phrase. But remember a million years ago when we were doing this here? And don't worry, you're not going to have to suddenly start doing this again. Remember that? Get that up there. And I tried to explain why the bottom was n-1. And I remember talking about the fact that it was an adjustment because it was a sample. Remember that? It was to adjust it to make it more true to what it should be. But it also, another way to look at it is, let me see if you guys can get this. If I have 4 numbers that average to 20, can anybody tell me anything specific about those numbers?
They should be around 5.
Careful now. If they average to 20, they should be around 20.
20. 2 need to be higher than 20 and 2 need to be lower than 20?
3 could be lower and 1 could be higher, as long as it's higher enough, right? You with me? So you can't say that, but I can say that they have to add up to be what? If I have 4 numbers, what's the only way they can average to be 20 if they all add up to be 80? Everybody with me? How do you find the average? You add them up, divide by how many there are. What's the only number divided by 4 that equals 20? 80. So I know that they must sum to 80, right? So if I wanted to, if I just said to you, make up a list where the average is 20. Make up a list of 4 numbers. You can go crazy for the first how many? The first one's 10, the next one is 71. Well, that sucks already. First one's 10, the second one's 21, the third one's 13.
Oh my God.
Now, can I make the last one anything I want it to be? No.
Not any.
So how many degrees of freedom did I have?
3.
1 less than the total number you had, right? So that's really what that thing is. It's a measure of what's called the degrees of freedom. So don't freak out when this list, if you look at the top of this column, you'll see it's called the degrees of freedom. So if I have a degrees of freedom of 45, how big was my sample? 46. So this is really just a measure of sample size still. Just be careful when you go to use this chart that you got to subtract 1 from your sample size. Okay. All right, so hopefully you guys all that. So here it'd have to be, what I have so far, 31, 44, so this would have to be 36. Cool. So that last one is restricted. I can't make it whatever the hell I want to. It has to be exactly what makes it work.
So it's like, it's the sum of the 3 previous numbers.
Subtracted from 80. Whatever needs to make it all the way up to 80. Cool. Yeah?
So if we have a sample size of like 56, we use 50 or 60 or...
You'll notice, that's a good question, and of course the details will come out as we do some more of these. But it's by 1 at first, because notice how much the t-scores are changing. They're changing a lot up here, right?
Yeah.
But then notice how little they're changing down here. So then they start saying 40 to 50 to 60, and then they start going by hundreds, because they really stop changing so much. Right? And it's that same idea of a lot of change and then not much change. We see the same kind of thing in the T distribution. A lot of change and then not much change. So that's why they go bigger. So in practice, you almost always go down, no matter what. So if I had a sample size of 56, I would go to 50, not 60,
Right.
to be more conservative, right? In practice, it actually, if you had 59, I think I'd use 60. Okay, so let's try this out. Let's see how this chart gets used. So if I want to be, let's say, 95% confident, and I take a sample of 24. and S is 11.891. What do I still have to tell you before you can go look up the t-score? There's one thing I haven't told you. I don't have to tell you the degree of freedom. You can calculate it.
Sample mean?
I don't have to know the sample mean just to look up the t-score, right? If I wanted a confidence interval, yes. But it has to be true to be able to use Z or T.
Normal.
Normal. So I got to tell you this is a normal distribution. What would the degrees of freedom be for this? 23. It's just one less than the number. No big deal. So degrees of freedom is 23. So, and what would alpha be? How much is in 2 tails?
5%.
And again, I really hope you guys get this. There's nothing major. If there's 95% inside, there must be 5% outside in the 2 tails, right? That tells me which column to look in. All right, let's see if we can find this t-score. The area was 0.05. N was 24, so degrees of freedom was 23. Looks to be 2.069. So that's the number you would put in there. Instead of a z-score, you would just put 2.069, and then everything else is the same. You find the error, you add it, you subtract it, they're all the same. We've seen that kind of thing happen a lot in here. We have one little tweak to a formula, but everything else is the same. So here, let's take a second and see if everybody can do this. Find these t-scores for these situations here.
2.0.
These are all normal, by the way. I'll go ahead and say that at the beginning. To be completely upfront, there's a trick question up there.
Oh.
You just got to figure out which one it is. Don't say it. So find the appropriate score. If we say that, that might help us out. For each of these situations. They're each normal, by the way. Call me over if you need some help. So let me just get right to the point first. Which one of these would you not use a t-score for?
Second one.
Second one, because why were t-scores invented?
Because we got a signal.
Say again? Why were t-scores invented?
So we can use it on a sample.
When I have S and not sigma, when I don't know the population standard deviation, keep that in mind. What tells me when to use a t-score versus a z-score is if I know the population standard deviation or not. You with me on that? I don't care how big the sample is. I don't care about anything. That's what tells me when to use a t-score or z-score, and we see that in the formula. X bar plus or minus z sigma, X bar plus or minus ts over square root of it. It tells you which one to use when.
So it's when we don't know what the population standard deviation is, but we know what our
S
sample
is. Exactly. What are sample standard deviation? So in this first one, what's the degrees of freedom?
36.
36. I want 98% confidence, which will be that second column, right? 2% in the outside. 36 is my degrees of freedom. So it looks like 2, 4, 3, 4.
Yep.
So T equals 2.434. This one I can use a z-score because I know it's normal. Cool. I didn't even have to tell you this one was normal. Why not? I didn't have to tell you that this is normal. Why didn't I?
Because
How big is the sample? Which is bigger than 30. Cool. So if I had a problem like this, I wouldn't have to say a word about being normal because you know it's normal. The sample's big enough. But it has to be normal. I either have to tell you or the sample's got to be big enough to be normal. So I don't need degrees of freedom here at all, do I? Z-score doesn't need all that crap. To be 80% confident, what's the z-score going to be? We figured that out earlier.
20% divided by
10%, you look at the 0.10. And actually, if you look at the bottom of this column,
2. It's negative.
z-scores are at the bottom of these columns, right? The z-scores are at the bottom. So isn't that 1.282, I think, in there? Cool. Remember, we got 1.28 because we can only get out to 2 decimal places. They're a little more precise here. 1.282. Do you guys start to see how the T-chart is a really cool place to go for z-scores? Because it's very detailed, and the z-scores are at the bottom. So a lot of times I'll be looking at a T-chart, and a student will say, why are we looking there? We want a z-score because they're at the bottom. Z-scores are at the bottom of this. Kicks ass. This is really detailed for confidence intervals. Yeah?
What happens if we have less than 80% two-tails?
Obviously, this chart is nowhere near complete. I mean, if I wanted to make it complete, it'd have to be like an atlas of the world or something. You see what I'm saying? Because I don't even cover like the real, I jump around a lot in the numbers. I jump around a hell of a lot in the percentages. So obviously this is not complete. Our calculators actually have the capability to give us precise t-scores for any situation. But I'm a big believer in starting here and then going there eventually. What about this last one? Which one do I use?
T-scores.
T-scores, cool, because I don't know sigma, I just know S. What's my degrees of freedom? 10. 90% confidence, so which column? Yeah, this guy. So my degrees of freedom is 10, 10%, 1.812, I like it. So the T-score here, that's weird, it had a bit of ESP, 1.812. And I really desperately want you to realize, nothing's changed really about the formula at all. It's just where do we get that score that goes in that spot? It's not a Z anymore, it's a T, but it's just the score that tells me how far to go away. That's all it is. It just comes from a different chart. And the chart's actually easier to use. So let me give you a complete problem to try.